In this video about the equation of a plane, we're going to look at two problems in particular. The first one is a line parallel to a plane, and how do we decide? And the second one, does a line or not lie in a plane? So just to remind you, we've been working on the equation of a plane, and that there are three forms that we can have for that, and we'll be using the one that's most appropriate in this case to help us solve the problem. The first one is we've got the vector form of a plane. Here we have the Cartesian form, and finally the normal form of a plane. So for the first problem, what I want to do is show that this line here lies or is a line that is parallel to this plane. So we've got a line, it's in 3 dimensions and it's in vector form. We're asked, is it parallel to this plane here that's given in Cartesian form? And as ever, it's difficult to draw diagrams to give us an idea about this, because the diagrams that we draw are in 2 dimensions. Now you can help yourself by trying to consider a plane as a piece of paper and perhaps a line as a pencil, just to be able to visualize the problem. I'm just going to have a look at this graphic here, 3-dimensional. And there we can see a line and a plane. So the line here and the plane here in purple. And they certainly look on this diagram to be parallel to each other. But how can we decide? How can we show that for sure? Well, if we go back to the equations, what do we know? What's important about being parallel? Well, parallel, we're talking about direction. So the direction of the line is easy. It's 4, 3, 1. It's parallel to that vector there. But the direction of the plane, well, we haven't got it, except that we've got the direction of the normal. So the normal in this case to the plane is a line that is perpendicular to the plane, and that would be 1, -2, 2. So is it possible to consider the normal and the direction of the line? Well, let's just have a look at a normal on here. So that's a point on the plane, and let me draw a normal line to that plane. So what can we say about the normal to the plane and the line? Well, hopefully you'll see there that those 2 lines there are perpendicular to one another, and that's the trick to being able to do this. What we're going to do is not show that the plane, the direction of the plane, is parallel to the line. What we're going to do is show that the perpendicular line to the plane, or the normal, is perpendicular to the line. Since if it's perpendicular to the line, then the plane is going to be parallel to this line. So the line has got direction (4, 3, 1), and the plane, well, the plane's normal is 1, -2, 2. Okay, so if you remember from that, we're getting that from the fact that r dot n is equal to a dot n. R is a general point on the plane, and n is our perpendicular vector to that plane, and that's going to be equal to 11 in this case. So we can see that the direction of the normal is 1, -2, 2. Right then, so what we've got to do then is show that 4, 3, 1 and 1, -2, 2 are perpendicular. How would you do that? Well, hopefully your answer is that if they're perpendicular, then the dot product of those vectors is going to be equal to 0. So that's really easy to show. And that's the key in many of these questions. The actual mathematics behind it here is very straightforward, isn't it? Finding the dot product of these two vectors, 4 minus 6 plus 2 is equal to 0. That's fine. But the tricky thing is the reasoning that goes behind it and being able to visualize the problem and work it through. Okay, so that's a good method to see if a line is parallel to a plane. The second problem was to consider if a line lies in a plane. So here again we've got the line is in vector format and the plane is in Cartesian format. Here's what it would look like. There we go, and that's, you can see very clearly there that does, but obviously what we want to do is show that that's the case. So how are we going to show that this line lies in the plane? Now we've done something very similar earlier on. What we did before was show that a point lied in a plane. I'll just remind you of the question where we did that. We were looking to see if 4 points were coplanar, and we had a plane involving 3 points, and we were checking to see if the fourth point was in that plane. And all we had to do was substitute the values of x, y and z into there, and to see if it gave us the value that we were after, in this case, which was 18. In that case it didn't, so that showed that this point did not lie in the plane. So in the example here we can do exactly the same idea. What we're going to try and do is show that this line lies in this plane. So there's my equation of the line, and I'm just going to write that in parametric form. So x is equal to 2 plus 5s. I'm being really careful with my s because it looks very much like a 5. Y is equal to 1 plus s, and z has got to be equal to minus s. Now for these to lie in the plane, that must hold true when we substitute those values into that equation. In other words, if we take the x coordinate and 3 lots of the y coordinate, subtract that, and add 2 lots of the z coordinate, we should get minus 1. If we don't get minus 1, it doesn't lie in the plane. So let's try that. X minus 3y plus 2z is what we're trying to find. So here we've got 2 plus 5s. Try that again. So x is 2 plus 5s minus 3 lots of y, so 1 plus s, and then we've got 2 lots of z, so that's minus 2s, and that should give me a value of minus 1. So 2 minus 1 there, 5s minus 3s minus 2s, all the s's cancel out, it gives me a value of minus 1. Therefore the line lies in the plane. Okay, so the actual mathematics that we do behind that is very straightforward. You've got to be a little bit careful with some simplifying, but the difficulty with these is the reasoning, and that's worth taking a lot of time to start with, just to make sure you understand what we're after in the question. So that's an example of seeing if a line lies in a plane, and the previous one was trying to see if a line is parallel to a plane.